Hello class, in this example we're going to show how you can do a one sample z-test for proportions. So let's go ahead and read this problem. It says, suppose a chocolate factory is curious to see if using robots to assemble boxes of chocolates is actually feasible. Now the factory decides to use a set of robotic arms to select chocolate pieces from a conveyor belt and assemble them in a box. Okay, so this first part is just kind of general information about the problem. Then it says, after a period of productivity, 500 boxes are randomly sampled and examined for defectiveness. What does defectiveness mean? It means missing or incorrect placement of pieces. So essentially the box is not put together correctly the way that the chocolate factory wants it to be. Of these 500 sampled, 17 were defective. So when they used the robot, 17 out of the 500 were defective. And currently, this work is done by human assemblers with a defective rate of 3.6%. So the factory currently uses human workers, and their error rate or defective rate is 3.6%. What we want to know is there evidence that the robots have a different proportion of defective boxes than the human workers? And we should assume a significance level of 0.05. So the first thing we should do is let's underline the important pieces of this problem. So first off, we can see under 500 boxes. Okay, so this is going to be my n. I'm going to just write this over. N is equal to 500. Just over to the side, are randomly sampled and examined for defectiveness. So randomly sampled is an important piece. We'll talk about that in just a second. And the thing that we're looking for is defective or non-defective. So what type of variable is that? Well, it's a categorical variable because it's a yes or no. Is it defective? Is it not defective? We can't describe this with a numerical measurement like, let's say, height or weight. And so it's a categorical variable that can be described by a proportion or a percent. So then we find out of these 500, 17 were defective. So this is essentially our number of successes. So x is equal to 17. We can think of this as the number of defective, or in the terms that we like to use for proportions, this is the number of successes, the things that we are curious about. Now it says currently the work is done by human assemblers with a defective rate of 3.6. This is going to be P naught equal to 0.036. And I'm going to convert this from a percentage into a proportion. It'll be easier to use in my calculations. So let's go ahead and talk about what my parameter of interest is. Now that we've gotten this information down, also we might want to put our alpha or significance level is 0.05. So our parameter value, so our parameter in this case, the unknown from the population is then P. This is the unknown population proportion of defective boxes when robots are being used. This is the thing that we want to test. And so once we know our population parameter, and this is always based on what type of variable we have. So in this case, our unknown is P because we're looking at a proportion. It's a categorical variable, and so we can describe that or summarize that using a proportion. So the unknown from our population will then, of course, be P instead of, let's say, mu, like it is when we are using means. Okay, so the next thing that we should do is we should set up our null and alternative hypotheses. So because our question is asking whether or not it's different, so our null will be P is equal to 0.036. That means that the proportion of the proportion of defective boxes when robots is used is just equal to that of when humans are used. And the alternative will then be P is not equal. Is there a difference between these values? So is different than 0.036. Now, before we calculate our test statistic, we should check the conditions for inference. So the first thing is that we should always check is whether or not our sample was obtained using some sort of random mechanism. And recall, I said, let's go ahead and underline this randomly sampled from the beginning, because this is something that we're going to need to come back to. So very importantly, our sample of 500 boxes was randomly sampled. So we can check that condition. Random sample and check mark. The other thing that we need to check when we're doing proportions is the sample size condition, which in this case is n times p naught, the claimed value, must be greater than 10, as well as n times 1 minus p naught must also be greater than 10. So let's go ahead and check this really quick. We have 500 was our sample size times our claimed amount of 0.036, and this is equal to 18. So since 18 is larger than 10, then this condition is met. Now let's do the same thing for the other condition. So 500 times 1 minus p naught, which in this case is 0.964, is actually equal to 482. Therefore, this condition is also met. Now that we have both of our conditions met for inference, we can calculate our z-test statistic. So remember, the test statistic is just the vehicle to get to the p-value. So first, if I calculate z, this is for a proportion. So my formula is p hat minus p naught, all divided by the square root of p naught times 1 minus p naught over n. So recall, p hat is simply just, I'll write it over here, p hat is equal to x, the number of successes over the number of trials. And so in this case, that was 17 over 500, which is then equal to, if I want to calculate it to a proportion, is 0.034. So let's go ahead and put this into the formula up here. So 0.034 is my sampled proportion, p hat. This is going to be the best guess or estimate for the true proportion. My proportion claim is then 0.036. This is then all divided by, all under the square root, 0.036 times 1 minus 0.036, which in this case is 0.964 divided by then 500, my sample size. So here for my numerator, I get a negative value of 0.002. And for my denominator, so this whole expression comes out to be 0.0083. And so when you are doing proportion problems, make sure that you carry your decimal out as far as really you can. 4 decimal places is probably fine, but this is where it really makes a difference, because you're dealing with such small values that it's important that you carry out your decimal points, because it can really change your last result if you round each step. So here you have your numerator divided by your denominator. You get then a z-test statistic of negative 0.24. Well, just looking at this test statistic, it's not very extreme. So what that means is that we're probably not going to see a very small p-value. So how can we calculate the p-value or find the p-value? Well, recall this is a z procedure, so we can look it up on a standard normal table. All standard normal distributions start at 0 or have a center of 0, and we're looking for a two-sided p-value because we're looking to see if there's just no difference between the two. So we need to get the upper and lower sides that's more extreme than our test statistic, and we find from the standard normal table, if we look it up for the area that falls below negative 0.24, for a z of negative 0.24, we get then this to be 0.40517. So because this is a symmetric distribution, that means the area that falls above 0.24 in the positive direction is then 0.40517 as well. So our p-value is the addition of these two. So the p-value, the total area that is more extreme than our test statistic, will be equal to 0.81034. So if we want to make a conclusion about this, then if we want to make our conclusion, then our p-value was quite large. So what that means is that we're going to fail to reject the null at a significance level, and I'm just going to abbreviate significance as sig. So sig level of 0.05. Recall, if our p-value is low, we reject HO. If the p-value is high, then the null is going to fly. So we're going to fail to reject the null hypothesis at a significance level of 0.05. And what does that mean? That means that there is no evidence that the proportion of defective boxes is different between the human worker at 3.6% and the robot. So what that might mean is because there really is no difference between defective, then some other choices can be made. Perhaps maybe getting the robots is an expensive investment at the beginning, but in the long run is going to be cheaper. And so perhaps because there's really no difference between them, maybe the cost factor will make the decision. So there's a whole lot of context that can go into problems more than just whether or not we reject the null hypothesis. Hopefully this video helped you understand how to do a one sample z-test for proportions.